Okay, so last day we were talking about reaction profile diagrams. And we said that reaction profile diagrams essentially come in three flavors. These, as a reminder, are plots of enthalpy against reaction coordinate. And if you imagine if you're going from an A2 plus B2 to give two ABs, then you can imagine a scenario where we absorb more energy than we give out. So A2 plus B2 gives rise to two ABs. And we absorb this much energy, and that energy is absorbed in breaking bonds. Remember, the breakage of bond requires the input of energy, and that's that part of the Morse curve. So this is the amount of energy we put in to break the AA and the BB bonds. This is the amount that we release when the AB bonds form. So if we consume more energy in bond breakage than we release when bond formation happens, we say this reaction is an endotherm. And essentially all that means that heat energy, this is enthalpy, right? The heat content, constant pressure, that heat energy moves into the system. How much heat energy? Well, this much. Right? So this, if H is on this axis, then this is your delta H. And again, remember, we define the delta of anything as the final state minus the initial state. And since the enthalpy of my product here, since the enthalpy of the product is a larger number than the enthalpy of the reactant, then here delta H is going to be, so here delta H, which is equal to HP minus HR, this is going to be greater than 0, right? In other words, it's positive. So this is an endotherm. There's a version in which the energy consumed in bond breakage is less than the energy released in bond formation, right? So we consume this much energy, but we release more. So that's the scenario, and again, this is H against reaction coordinate. So this is a scenario where it's called an exotherm, and the delta H of the reaction is that value. That's the delta H. And here, delta H is going to be less than 0. In other words, it's negative, because the enthalpy of the product is a smaller number than the enthalpy of the reactant. So here, heat is lost by the system. And then the last scenario describes what's called a thermoneutral, right? A thermoneutral case where the energy absorbed exactly equals the energy that's being released. I'm going to make 2 points here. One is that you notice when we're doing a plot, I'm very deliberate in terms of labeling the axes. If you don't label the axes, I don't know if you're plotting bread against butter, boys against girls, red against green. And remember, we talked about this in class, your job as a scientist is to communicate effectively, right? And clearly. So I'm not going to try to guess what it is you're plotting, right? You have to tell me what you're plotting, okay? That's point one. The other point I'll make, which is a bit more useful here, so I should have said, here delta H is equal to 0, because the HP is equal to HR, right? But the other point I was going to make is that you want to be very careful in the language that we use to describe what is happening. So I'm very deliberate in saying that we are consuming more energy in bond breakage than we are releasing in bond formation. I never said that we're breaking stronger bonds or that we're breaking more bonds, because we don't know. All we know is that we're putting in more energy. Now that could mean that the bonds we're breaking are stronger than the ones we're making, or it could mean that we're simply breaking more bonds than we're making, or some combination of the two. I don't know that for sure. All I know is I am spending more than I'm getting back, right? And there could be several reasons for that. I don't know what they are without knowing who A2 and B2 and AB are. But all I can say is that we're expending more energy in bond breakage than we are getting back when bonds are forming. And so it's important then, when we are doing chemical reactions, that one of the things we want to get from a chemical reaction is the delta H of the reaction. So how exactly do we do that? And let me just say while we're on it, if I look at a chemical reaction, there are, at least from an energetic perspective, there are several features of the reaction that are of importance to us. So again, here is the reactant, and here is the product. And this entity on top, we're going to call this the transition state. Right? We're going to call it transition state, or the TS. There are two energy gaps that are of interest. One is the delta H of the reaction, that's called the energy change of the reaction, or the delta H of the reaction. But the other is the gap between the reactant and the transition state. This is called the activation energy. This is called the activation energy of the reaction. And this one controls the speed of the reaction, the rate of the reaction, the kinetics of the reaction, which we look at in a couple of weeks. This one controls, to some extent, the position of equilibrium, essentially how far the reaction goes. Okay? And for the next rest of this lecture, we'll talk about the delta H. The activation energy is a parameter that we will look at in about somewhere close to mid-semester when we start doing mechanisms and kinetics. So how do we go about determining whether a reaction is exothermic, so it can do work warming something up, whether it is endothermic, so it can cool a system, or whether it's thermoneutral? And the answer is we need to work out those values with the bond energies. Now, I've posted this document on Blackboard. It's under Documents, I think. And I'll send you guys an email to tell you where it is. And you need to print this out to follow along to see where I get the numbers. Okay? So let's imagine, if you recall, the very first thing that we asked is what is the delta H of the reaction for the burning of methane to give carbon dioxide plus water. So in order for us to do that, and we know, for example, the reaction is an exotherm, but we're going to work it out, I have to have in my mind what it is that is happening. So again, we are going to divide the process into two parts. We're going to calculate how much energy I put in to break bonds, and then we're going to calculate how much energy is released when the new bonds form, and we're going to basically add the two numbers, right? So we're going to say energy gained in bond breakage, because it's being gained, is positive. Energy lost in bond formation, and that's going to be a negative number. And if I add those two, that will be the delta H of the reaction. So I'm going to use my table of standard bond energies to determine how much energy was consumed in bond breakage, how much energy is lost in bond formation. So I'm going to split this up in the following way. I'm going to say bonds broken. I'm going to identify those, and then I'm going to say energy gain. Right? So what bonds are broken? Well, what I'm going to do is I would have to draw these molecules out. So if I don't already know, methane is CH4, oxygen is O single bond O, carbon dioxide is C double bond O double bond O, and water is this. So I'm going to draw out my reaction as such. So which bonds are broken, right? What are we putting in to climb the ascending portion of the plot, where bonds are being broken, right? So we are breaking 4 carbon-hydrogen bonds. We are also breaking 1 O-O bond. And so once we've broken these, right, that's the full menu, the full inventory of bonds that are broken. So I'm going to go to the table and see how much it's going to cost me to do those. So if I look at CH, it tells me a CH bond is 99 kilocalories per mole. So this is 4 times 99 kcal per mole. Plus 1 times the OO bond is 35 kilocalories per mole. So the total energy that I have consumed in bond breakage, so this is 400 minus 4, so that's 396. That's 401. This is 431. 431 kilocalories per mole. In other words, I can say, in a simple-minded perspective, because this gets a bit more interesting, that essentially going from here to here, that represents 431 kilocalories per mole, right? That's essentially what that is. That's the energy I put in to break all the bonds. Good. Well, I'm now going to ask bonds formed. Because up until now, we've just climbed to the top. We haven't completed the bond formation part yet. So let's do an inventory of the bonds formed and of the energy lost in the process. So what bonds are formed? Well, we formed 2 C double bond O's. So we formed 2 C double bond O's. And we formed 4 OH bonds, right? So each water molecule has 2 OH bonds. So in total, I formed 4. Okay, good. That's a complete inventory of the bonds that we formed. Okay. How much energy did I lose in the process? So as bonds are being formed, the system loses energy. How much? I'm going to go to the table. Now you notice that when you go to C double bond O, there are a whole bunch of them. There's one for carbon dioxide, so this is the far right of the table. There's one for carbon dioxide, there's some for things called anhydrides, ketones, esters, amides, halides. You will, when we get, this is about another 2 weeks, we'll start talking about more functional groups and families of organic compounds. And so you know what an aldehyde is, what an anhydride is, and so on. In any event, you notice the difference in the values is really very small. It's like a 2 kilocalories per mole difference, except for carbon dioxide. So the value for carbon dioxide is 192. So this is 2 times 192 plus 4 times OH is 111. And I'm just going to say all of this is kcal per mole. So this is 444. This is 644. You know what? It's too late in the afternoon. So this is going to be 444. 444 plus 2. So that's going to be equal. Not copy, right? 444 plus. Yeah, that's better. That's 828 kilocalories per mole. Okay? My delta H then is the sum of these two numbers, recognizing that energy gained is positive and energy lost is negative. Now, the nice thing with this approach is that it doesn't matter then whether you say it is this followed by that or this followed by that. It doesn't matter. If I write it as minus 828 plus 431, it doesn't matter, I'll get the same number, right? And the same sign. So the delta H then is simply the sum of the two numbers, recognizing that one number is positive and the other one is negative. So that turns out to be 397, or negative 397 kilocalories per mole. That is a delta H of the reaction. So we spent or we gained 431 to break the bonds, and then we got 828 when new bonds were formed. So overall, the delta H, the change, is a sum of plus 431 and negative 828. So this reaction is exothermic to the extent of 397 kilocalories per mole. Let's do another one. Let's work out the delta H of reaction, and I'm going to keep this. I'm going to keep this format because we use it over and over again. Let's do a different reaction. Let's consider the delta H concerned with taking, let's see, let's take CH3CN plus H2 to make CH3CH2NH2. Okay? So what is the delta H of that reaction? Well, first things first, we've got to figure out what more molecules look like so we can tell which bonds we've made and which bonds we've broken. So CH3, C triple bond N, CH3CN looks like this. So it's CH3, C triple bond N plus 2HH give rise to CH3, CH2, NH2. Okay. Well, which bonds were broken? Now, chemistry involves change. So I'm interested in the bonds that underwent change. So I have CH3 in my starter material, my reactant. I've got CH3 in my product. This part of the molecule didn't change. So because it didn't change, I don't have to go and invest time in determining, how much energy is involved in breaking those CH bonds, because they didn't break. So I'm not breaking those bonds and reforming them. They are just spectators. They were not involved in the chemistry. I'm going to ignore them because I should. So in my starter material, I have my CH3 remains intact. This bond between the C and the C remains intact. But whereas this carbon had 3 bonds to N, now it only has 1 bond to N. So I broke 2 of these bonds. Okay? I also broke the HH bond between the dihydrogen atoms, the atoms in dihydrogen. And I broke 2 of them. Right? So those are the bonds I broke. What bonds did I form? Well, I formed 2 CH bonds. Those weren't there at the beginning. I did not form this CN bond. This CN bond was there at the beginning. It was one of 3. I killed the other 2. Well, I broke the other 2. I also formed 2 NH bonds. So the bonds that I broke are 2 CN bonds and 2 HH bonds. The bonds that I made are 2 CH bonds and 2 NH bonds. So I'm going to go to the table. Now if you look at the table, it's not going to tell me what is the energy required to break these two bonds. What it will do is tell me the energy of C triple bond N, and the C triple bond N is 213. The C single bond N is 73. So the second column, third entry down. So the difference between the triple bond, which is 213, and the single bond, which is 73, that difference is the energy involved in breaking these two bonds. So the table doesn't give me the energy of those two bonds, but it tells me what the C triple bond is, what the C single bond is, and therefore the difference is the energy required to break those two bonds. So the bonds broken would be 2CC, and we're going to call these pi bonds, which we talk about, 2CN pi bonds. I'll talk about that in a second. Plus 2 HH bonds. Those are the bonds broken. Now, really fast this, and you would have met this in Gen Chem. If I have an XY bond, and that bond is a single bond, then we say that bond is sigma. That's a sigma bond. If I have an XY double bond, one of them is sigma, and the other one is pi. If I have a triple bond, one of them is sigma, the other two are pi's. And we will talk about these in some more detail later on when we do hybridization, which you may have met in Gen Chem. But in any bond, one of them, in any XY bond, if it's a single bond, it must be sigma. When the bonds are multiple bonds, one is sigma and the others are pi. And there's no convention as to whether it's the bottom one is sigma or the top one is pi. It doesn't matter. One is sigma, one is pi. So in this triple bond, there are two pi bonds and a sigma bond. This is a sigma bond. So I kept the sigma bond, I just broke the pi's. Which is why I said here that the bonds broken are 2CN pi bonds. Nowhere in the table is there a value for 2CN pi bonds. There's a value, by the way, for C double bond N, but that's not the right one because one is sigma, one is pi. And I broke two pi's. Right? So I want the difference between, because obviously I want the difference between a sigma and a pi and the sigma. So when I subtract, what I get are the two pi's. Okay? Okay, so how much energy then is involved in bond breakage? For the CN, this would be the 213 minus the 73. And I'm just going to put all of this as kcals per mole. Plus 2 times the HH bond is 104.2. And this is kcal per mole. And that total is let's see, so that's 208.4 plus let's see, that's 30, that's 40, that's 150 plus so that's 348.4 kcals per mole. Okay. Yeah. Okay. What bonds are formed? Well, we formed two CH bonds plus 2 NH bonds. Energy lost, the CH bonds are, was it 111? The CH bonds are, no, 99. The CH bonds are 99. And I'm just going to make this kcals per mole. The NH bonds are 93. This is kcals per mole. So that's 198. This is 6, that's 204, 294, 384. That's 384 kcals per mole. So my delta H is the sum of those numbers. It is minus 384 kcal per mole. Right? That's for the energy lost. I'm just going to add them, bearing the signs, plus 348.4 kcal per mole, right, which is the amount of energy I've put in. And so that is going to be exothermic to the tune of, that's 40. It's too late in the day. So 384 minus 348.4, that's 35.6. That's negative 35.6 kcal per mole. Okay? Right, so we would determine then how much energy, and so if you asked to sketch the plot for this reaction, you would just say, you know, you would put the axes, so H against reaction coordinate, and then you would have CH3CN plus 2H2, that's a reactant, and then your product would be CH3, CH2, NH2, and then you draw this, and you tell me that this value is 35.6 kilocalories per mole. Right? So that would be a plot, a sketch of the reaction profile diagram. Okay, so that's essentially how we use the table to calculate the delta H values for reactions. We want to talk a little bit now about reaction profile diagrams in a little bit more detail. And what we do is go back to our very simplified diagram, which draws a single curve, single hump for the reactions. And it turns out that many reactions do not occur in that simple a fashion. Now, it will not matter in terms of the calculation of delta H, right? That is not going to be an issue. So you do that in exactly the same way, making the simplified assumption that we're determining how much energy is put in to climb the hill, and then how much energy is released when we fall down the hill into product. That will always remain the path we take to get the delta H values. And in some cases, I'll draw the bonds out for you so you can see which bonds are broken, which bonds are formed, so you can do the calculation. But let's go back to our reaction profile diagram. And what I drew in the simple case was a scenario where we had, let's say, a plot like this. So I have reactant, transition state, and product. Well, every time we do a curve, for every hump, we consider that a step in a reaction. So if I look at this, I would say this is a synchronous which is the same as concerted, which is the same as single-step reaction. I can also say it's an endotherm. So if somebody asked me to describe that plot, I would say that is a synchronous endotherm, or a concerted endotherm, or a single-step endotherm. A step involves going from a minimum to a minimum. What does that mean? This is a minimum on the plot. That's a maximum. That's a minimum. So the two minima, the reagent and the product. A step in a chemical reaction is moving from one minimum to the next minimum, right? So that's what's called a step in the reaction. So I'd call this a synchronous or one-step endotherm. You'll notice if there's a single step, there's only one transition state. But I could have gone from reagent to product in entirely different ways. It might be possible that I'm going to go from the reagent to the product in an entirely different way. And I'll have H and reaction coordinate here. Now, I'm going to make the point. You notice how very deliberate I am in writing out reaction coordinate. Right? On the exam, if you're asked to sketch the plot, you're going to get maybe half a point out of some number for the axes. If you don't label the axes, you're just tossing away points, right? And you don't want to do that. I mean, there are valid places in an organic exam to lose points. This is not one of them. Okay, I mean, you just don't toss away points. So what are the species in a plot of this nature? Well, again, this is my reaction. That's my reactant. This would be called transition state 1. That's the first transition state. This is transition state 2. The transition states are the maxima on the plot. This is my product. The minimum between transition states is called an intermediate. So now, if I had to write this reaction out, what's actually happening is I'm going to go, it's step 1, minimum to minimum. I go from reactant to intermediate. In step 2, I'm going to go from intermediate to product. Right? So that actually would be a stepwise, basically a two-step reaction. And by the way, if I add these steps together, this is present on both sides, and the overall reaction is that reagent goes to product. So if you ask me to describe that reaction, I will say this is a two-step